We're going to now look at some special operators of systems. These can be handy in certain situations, and so we're going to go ahead and define them here. Special operators. The first operator is called the conjugate system, and we're looking at this in continuous time. We'll look at it in discrete time in just a minute. The conjugate system, so G tilde of S, is defined to be G transpose of minus S. So instead of having just S here, we have minus S. So you can go through and show that it can be written this way. If we just take the transpose minus S, this is what we get. So here I've used the adjoint as opposed to transpose. But in general, in this case, the matrices A, B, C, D are real, so these will all be just transposes. I use the adjoint here just to kind of give us the flavor that this is related to conjugate, complex conjugate types of stuff. So in the case when a matrix is real, its adjoint is the same as its transpose. Okay, so an ABCD system becomes like this. Minus A adjoint, C adjoint, B adjoint, D adjoint. Okay, so notice that the A matrix are where the poles are located. The poles are of the system A now, and this are related, obviously, because it's the same A. But in this case, it's minus A adjoint. It turns out that the eigenvalues for a matrix are the same as the eigenvalues for its transpose. So those are the same. However, when I multiply by a negative sign, it negates all the eigenvalues. So what happens then is, in general, my matrix A may have some constellation of poles if you were to plot them. When you do this, minus A adjoint, they become the mirror image of those poles with respect to the imaginary axis. For discrete time, we have a similar situation. We have G tilde of Z is equal to G transpose, and instead of saying minus Z, we're doing Z inverse. So when you go through and you plug that in and simplify, this is what you get. It becomes more complicated. So this is what you get. And so the ABCD matrix system becomes all of this. And notice that it requires A inverse, A adjoint inverse. Okay. So if A is a singular matrix, then obviously I cannot do this. It turns out that happens to be a very special case, but it is possible. So it's more complicated in discrete time, basically. That's what this is showing. Now, in continuous time, the poles of the conjugate system were mirror images with respect to the imaginary axis. In discrete time, they become kind of a mirror reflection around the unit circle. So if I have a pole inside the unit circle, I'm going to have the conjugate system is going to have a pole outside the unit circle, and they're going to be like mirror images of each other. So that's what happens in discrete time. So what's the point of the conjugate system? The conjugate system kind of acts like an adjoint system. So we've talked about an adjoint of matrices. We haven't actually talked about adjoint of systems. We will talk about adjoints of systems, but for now, let's see how this works. So, for example, if you want to compute the magnitude of the transfer function along the stability boundary, S is equal to j omega, in continuous time system, G of j omega norm squared is the largest singular value of the matrix G of j omega squared. But this singular value squared is given by the largest eigenvalue of this product. Okay, so notice that this is the complex conjugate transpose of this. Okay, so the eigenvalue of the complex conjugate transpose times the matrix, that largest eigenvalue is the largest singular value of this matrix. But if you notice this quantity, this is actually what we call G tilde of J omega. Okay, so by defining G tilde of J omega, we have set ourselves up to be able to use it here. And we can even get a state model for this product, and I'll show that in a little bit. In discrete time, the stability boundary is the unit circle where z is equal to j omega. Okay, and so the 2 norm squared of the transfer function is given by the largest singular value of this matrix, and this largest singular value is equal to the largest eigenvalue of this product, where this is the complex conjugate transpose of this. And this quantity is what we call G tilde at e to the j omega. Okay, so using the same j omega, we get G and G tilde, and so we've seen how to do that. So if I look at this quantity as a quantity, I can write down the state model for this quantity, and it's actually given here. And for this quantity in discrete time, I can write down its state model, and this is what we get in discrete time. Okay, so later on, we may want to use this when we are working with magnitudes of transfer functions. That is, norm of the transfer function. The system left inverse. Suppose that D has full column rank, that is that D pseudo-inverse D is an identity. Then for G pseudo-inverse, defined this way, we can show that G pseudo-inverse times G is identity matrix. And it's like, wait a second, hold on. G has poles, and G pseudo-inverse is going to have poles associated with this. So how is it possible that when you multiply these two things together, I get an identity matrix that has no poles? This has no poles. It's a constant matrix. How does that work? Well, we've already seen we can do a similarity transformation on a system. So I take this system, I would concatenate this, that is, I would put this in series with G and form the overall state model, and this is what I would get. This is the overall state model I get when I put them together like this. Okay, so this is the overall state model. I'm going to do a similarity transformation. Now, when you do a similarity transformation on a system, it doesn't change a system's poles, eigenvalues. It just kind of rearranges the states. So I'm going to take the system matrix, multiply on the left by this, multiply on the right by the inverse of this. This matrix is actually the inverse of this matrix. And when I do, I get this matrix. And you're going, okay, why is this giving me the identity matrix? Well, I'll leave that for you to show. But if you go through and compute, the transfer function for this system, you will find that you just get the identity matrix coming out. So that's the left pseudo-inverse. For the right pseudo-inverse, we get a similar kind of thing, but notice that in this case, D times D pseudo-inverse is an identity. Instead of D pseudo-inverse D, we have D pseudo-inverse. So notice the form of the system inverse is the same as what we had before. The difference now is that G pseudo-inverse is equal to the identity, as opposed to G pseudo-inverse G. I mentioned similarity transformations, and we saw similarity transformations when we looked at modal decomposition or Jordan decomposition. In that case, the similarity transformation was associated with the eigenvalues or the generalized eigenvalues. So, in general, we can change the coordinates of the system. So, for example, we could let W equal a transformation matrix times X, where determinant of that transformation matrix is not 0, which means basically we're not losing any information in going from this transformation. So now W is related to X. How is the state model associated with W related to the state model associated with X? So, well, if we differentiate this equation, W dot is equal to T times X dot. But X dot is equal to AX plus BU. I distribute T through, and I get this, where I have replaced X with T inverse times W. T inverse times W. Likewise, Y is equal to CX plus DU. X is equal to T inverse times W. The new state model now has TA T inverse, TB, CT inverse, and D as its state model. And you can go through, if we define the system matrix this way, A, B, C, D. So notice I didn't put the little dividing lines in here. You can show then that the state model associated with this can be written this way. I take this matrix, and in a sense it's inverse, and multiply it out. And so this then is what happens when we use a similarity transformation. We can now talk about something called a linear fractional transformation. A linear fractional transformation, or LFT, has two forms. There's a lower LFT and there's an upper LFT. And it really is based on the diagram that you're working with. So in this case, I have a system with transfer function this way. Here I have specified two separate inputs. These inputs may not be scalars, they may be matrices, vectors, and these outputs may be vectors. Okay, and so delta is something that's being introduced here. And so the transfer function G, so G is all of this stuff associated with delta, is given by this expression. Okay, so what is this expression? This expression is what you get when you let U2 equal delta times Z. Okay, when you set that equal, then you just have a single input U1 and output Z1. And the transfer function from U1 to Z1, when I do this, is given by this expression. So that's what the linear fractional transformation is all about. It's all about giving the closed loop transfer function to a system. Okay, and so we can actually write that this way: Z1 and U1, linear fractional transformation. Okay, so this is the lower LFT. We can also have the upper LFT, where instead of feedback occurring down here, feedback occurs up here. We have this upper LFT, and so I can work with it this way. So the linear fractional transformation is useful if we have something that's in feedback, and we'll be using this kind of thing as time goes on to analyze a system with uncertainty. So delta U, the U here stands for uncertain. So we're going to come back and look at that, where that matrix transfer function is uncertain. We can get really complicated and work with something called the Redheffer star product, where we start with a P matrix and a K matrix of transfer functions. And the star product of these two transfer functions is given by this expression. Notice that it uses the lower linear fractional transformation and the upper linear fractional transformation, and then it has these two other terms. So suppose a matrix that's defined like this, where each of these may themselves be matrix transfer functions. Each of these may be matrix transfer functions. I can write state models for both P and K this way. Okay. And so notice that both P and K have these D terms, A, B, C, D terms. Notice I have 2 inputs and 2 outputs, 2 inputs and 2 outputs. So it can be shown that the Redheffer star product has a state model given by A hat, B hat, C hat, D hat. And what are A hat, B hat, C hat, and D hat? They're given by these expressions. Wow. So notice that A hat is the Redheffer star product of these 2 guys. But now, instead of being a system, this is not a system. This is actually just a matrix. Okay, this is just a matrix. So it's not a system. Okay, as opposed to here, where P and K are systems, I can define this Redheffer star product on just matrices. So these are just constant matrices. Once we're all done with that. Now, so this is really complicated. Where would this kind of thing even be used? Well, it's actually used in a situation like this, where we have an input that comes into the system. This system has 2 outputs. One of the outputs gets fed into this system, which also has an input. The other output feeds back into this system, and so this can feed through there, which feeds through there, which feeds through there, which feeds through there. And anyway, it's complicated because of all that interaction. And so the result then is I have resulting 2 inputs and 2 outputs that come into this overall thing. So whenever I do something like this, it's just going to be really complicated. And the Redheffer star product takes that into account. We won't use it much. I just wanted to give you an example of how you can combine systems in various ways. So this is the interconnection of systems and also special operators. So the star operator, we looked at the conjugate system and also the inverse system or the pseudo-inverse system.